starting shortly. So first, an introduction. So welcome at the, I think, fourth Web3 Kraków meeting, as always, at Software Mansion office here in Kraków. I'm Artur Michałek, your host for today. We're gonna have three exciting talks this afternoon. One will be remote, and two of the rest of them will be in person. And first, before we start, some important information. So first of all, if anybody needs to go to the restroom, they are located in front of me next to the elevators on the way you entered. In the kitchen behind me, we have two fridges with alcoholic and non-alcoholic drinks, so feel free to just take anything and serve yourself. After each talk, we'll have a short Q&A session. You will have time to ask your questions. And also after the meetup, we'll have pizza, so feel free to stay with us to chat and network. So that's all for the basic information. And first of all, Sasha from Nimbora will be joining us for a talk about Empower Ethereum DeFi Scaling with Nimbora. Please welcome him.
Can you see the screen? Okay, so I'll start. So hello everyone, so I'm Sasha, building Nimbora. So Nimbora is a cross-chain yield infrastructure, so it's basically allowed to access Ethereum DeFi, but from layer 2. So before diving into Nimbora, I'd like to give a bit more, to give a bit context about the issues that we are solving. So as many of you may know, on Ethereum you have DeFi. So basically everything that is in traditional finance can be coded and deployed on Ethereum. So you can do many stuff in DeFi, including doing some swap, trading option, lend your crypto, borrow some other asset. So yeah, and it's a big market. So this is like the total value locked on Ethereum. So this is something like significant. So Ethereum DeFi is good, but not for everyone so far. So if you want to interact with Ethereum for any to interact with any DeFi protocol, you'll have to pay some gas fees. So it can happen that these gas fees reach high level. If everyone wants to interact at the same time, the chain can be congested, which increase the gas fees. So if you if you want to invest just $1,000 of any crypto into DeFi for a 10% annual yield, and you deposit your crypto, just the gas fee will cost you 10% of your capital. So this is an issue. So here is the median of the gas price of Ethereum gas price. So here, so if you want to deposit your crypto to earn some yield, you have to deposit, but also redeem your token at some points after earning yield during a certain period. And same for borrow repay. So this is the gas that you need to spend to handle those operations. And based on gas price of 40 GUI and an Ether price of $3,000 per ETH, this is the cost, this what you will have to pay. So this is an issue because it doesn't make DeFi really inclusive. So it's kind of dedicated for users that have a big portfolio, that have a big fund. So it's really complicated to scale for anyone to interact with Ethereum DeFi. So a solution to scale Ethereum is to use a layer 2 network. So you have many different type of layer 2. Basically, it's it allows you to interact with the chain, but cheaper. But you are not actually you don't have access to Ethereum state. So like each rollup, each layer 2 has its own liquidity, has its own state. So you have different types of rollup. You have optimistic rollup, ZK rollups. I won't enter in the details, but yeah. So you can, like as Ethereum, code some financial stuff and deploy those. But the thing is that most of the liquidity is still on Ethereum, and layer 2 ecosystem can be immature. They don't have all of the protocols that has Ethereum. And yeah, sometimes if you want to perform a swap or to do any operation, it can be more expensive because there's not enough liquidity, or you may not have access to the same protocols that on Ethereum, especially if the layer 2 is not EVM compatible. So it's harder for layer 1 protocols to build on those layer 2. So what we want is actually accessing a rich DeFi ecosystem, so Ethereum, but at layer 2 costs. So that's all about Nimbora. Nimbora is Starknet based. So on Starknet, you have some DeFi apps, and what we want to bring is the rich DeFi ecosystem of Ethereum on Starknet. So we're going to see how we can do this. So the first approach to access Ethereum DeFi from Starknet would be to use a zapping protocol. So zapping protocol just allow you to access Ethereum yield. So you will have to deposit some. You choose basically a strategy. So let's say a earn vault. You deposit some ETH on the in the zapping protocol. So down the line, it will bridge your token to layer 1. There will be a relayer that withdraw tokens from the bridge and deposit it into the strategy and bring you back tokens on layer 2. So the issue with this is that it's not actually solving the gas cost, because finally you will pay gas cost for layer 2, gas cost for layer 1, and probably some additional cost for the third party, for the protocol, that zapping token. And also it's asynchronous, meaning so you deposit your ETH and you'll get your share of the yield strategy later on after some delay. So what we are doing at Nimbora is batching user transactions. So better than just zap transaction per transaction, we are going to accumulate user transaction into to a batch, so we can compare it to kind of train. So you have a wagon, you have many users that go in, and when you have sufficient amount of user in, then finally you send the big deposit amount on layer 1. And then you bring back on layer 2. So for 100 users, you can or more, you can save a lot of gas. So the gas cost, the final gas cost will be the Ethereum gas cost for a deposit divided by all of the users in the batch, in the wagon. So this allows us to save a lot of gas for user while being able to interact with Ethereum DeFi. Another concept is netting. So if you have some people that want to deposit, but also some other people that want to redeem, better than handling directly one deposit and one withdrawal on Ethereum, you can directly you can directly net those users on layer 2. So this allows us to save some gas as well. So our first integration based on those two concepts is Liquidity. So for those that do not know Liquidity, it's a borrowing protocol based on Ethereum. So you deposit some Ethereum as collateral, and you'll be able to borrow LUSD, which is a stablecoin. And yeah, so this is our UI. So you borrow into a certain amount of Ether, you submit the transaction, and yeah, that's it. So this, oops, sorry. So this is, so we solved the first issue of the gas cost. So basically you interacted with a DeFi protocol on layer 1 from layer 2 at layer 2 cost, but you still have this asynchronous issue. It will take some time to bridge. It will take some time to verify stacknet transactions. So on layer 1, and yeah, this is not good for user experience. The user directly want to get his LUSD. If he deposits, he directly wants to get his yield-bearing tokens in his wallet. So yeah, so when a user wants to deposit some token into a yield solution on layer 1, this is basically the process. So you deposit it, Nimbora will wait to have more users in the wagon, in the batch. When there are sufficient amount of users, it will bridge to layer 1. So the bridge, so it takes some time to validate stacknet transaction on layer 1. So this way, bridging layer 2 to layer 1 can take up, it's between 8 and 18 hours, so it can depend. Then you harvest on layer 1 tokens from bridge, you deposit into a strategy, and then there is the you have to bring it back to layer 2. So you have so the delay is shorter for layer 1 to layer 2. And then when tokens are ready on layer 2, we handle the response and distribute to the user. So this is a long process. Users do not want this. What they want is actually directly receive their ex-yearn Ethereum tokens. So to resolve this issue, we've built what we call the YieldX. So it allows a user to access layer 1 DeFi application synchronously. So what we did is that better like before to handle a transaction, a batch of transactions, send it to layer 1, and then send it back to layer 2. We directly we are able to measure all the holding of the yield strategy, meaning that we directly know the price of a share, the share token. So this is calculated with the tokens, the Ethereum that are on layer 2, the Ethereum that are transiting in the bridge, and the Ethereum that are on the strategy. So we've built vaults that have shared liquidity, some on layer 1, majority of it on layer 1, which is actually in yield, working to generate some income, and yeah. So if we know the total value of the vault, the total holding of the vault, we are able to price the share. So that's why we can handle directly the user request. So the user will deposit some ETH into Nimbora ex-yearn ETH token manager, which like manage the accountability. And because we know the total asset held in a strategy, we'll be able to mint a certain amount of share token and will directly send it to users. So that's how we solve this asynchronous issue. So basically with the YieldX, people can mint any layer 1 yield natively from Stacknet. So yeah. So this is the complete architecture. It can be a bit scary, but basically you have we can deploy any layer 1 strategy. So we have a factory that will deploy a package, so a token and a token manager. So token manager is the entry point for user to mint layer 1 yields, and the token is actually what represents the yield. So we have the pooling manager that that will gather all of the requests for this all of those strategies. It's modular, so basically this can handle some strategy, some ex-yearn strategies, some Aave strategies, some compound strategy, whatever. So it will just loop over all of the deploy strategy and send requests to layer 1. So the request can be a deposit request if you have a lot of people that actually want to generate yield. It can be a withdrawal request if you have in the contrary a lot of people that want to withdraw. And you have also another request, which is do nothing, because basically depositors and withdrawers are matched, and so we don't need to do anything. So we are going to hash all of those request data, send it to layer 1 via Starknet messaging, send the liquidity via canonical bridge. So after like something like 12 hours, data and liquidity will be available on layer 1. So we are going to loop on all of our layer 1 strategy adapters, and we'll bring more liquidity, we'll withdraw liquidity depending of the request. And when this is done, we're going to send back to layer 2 a token if there were some withdrawal requests, and data also. We need to tell the layer 2, okay, this is the new net asset value of the yield reserve. This is important because we need to be able, for user to be able to mint synchronously, we need to know the total net asset value, and this require to know the layer 1 net asset value. So the value in our reserve. So yeah. So we are going to launch this project very soon. So if you guys have some tokens on Starknet, wait for Nimbora to launch. We have some nice API and some points to distribute to users. So yeah, if you want to follow this, just follow us on Twitter, follow us on join our Discord, and yeah. So if you have any questions, feel free to ask.
Yeah, if there are any questions, I can just pass the mic. All right. If there are no questions, then thank you, Sasha, for joining us for this talk. And yeah, we'll just go through the next one. So right now, Tomasz Miśkowicz from Software Mansion will join us for a talk about IPFS.
Okay, so hello, my name is Tomek, and I'm a software engineer here at Software Mansion. And I am currently in the Starknet developer tools team, and I've been working on many of those tools. So yeah, my today's presentation will be a very basic introduction to InterPlanetary file system. So I had to learn all of this for the purpose of the presentation, so please bear with me, I'm no expert. And starting with the definition, IPFS is a modular suite of protocols for organizing and transferring data designed from the ground up with the principles of the content addressing and peer-to-peer networking. This is the definition taken from the docs of IPFS. And from the definition, we can see that there are two main key points. That the IPFS is based on content addressing and peer-to-peer networking. Content addressing, we'll get into that in a minute, but peer-to-peer networking, you may have heard about it sometime, like something like BitTorrent, downloading a torrents, you may have heard about it. So yeah, what does it even mean? In the traditional network, it's basically centralized, so if you host a file, you probably host it on like Google Drive or somewhere else, and the server is proprietary to Google. You go to you send a request to the Google server that you want to take the JPEG file, and then you get it as a response. And in the peer-to-peer network, all of the peers or nodes, I will be using the terms interchangeably, are connected to each other so that they don't have to connect to the one main server. They can just ask one of the peers in the whole network. So yeah, what are the problems with the traditional networks? the main problem is that it is centralized. So if the server dies, nobody can retrieve the JPEG file and basically cannot connect to the server. So the data becomes virtually inaccessible, and all of the responsibility to ensure the availability lies on the server operator. And in the IPFS, in the peer-to-peer network, it removes the dependence on the single point of failure. So if one, that's what I was talking about. So if the server dies, nobody can get the file. But in the second scenario, when we, for example, one of the peers that has the JPEG file dies, and if we are this peer marked as green, we do not have the connection to the peer that died, but still can retrieve the file from the other peer that has the file. So what are the other problems? Geographical limitations. So in the traditional network, the data has to be fetched from sometimes from long distances. For example, we're here, and if I wanted to get the contents from the file from, let's say, Australia, and if I have a poor bandwidth, it might take some long time. So it leads to latency issues. In the IPFS, the data can be fetched from the nearest node that has the file. So let's say the nearest node that has the JPEG file isn't on the other half of the globe. So for example, 500 kilometers away. So if I have the poor bandwidth, it will make a huge difference for me. And as I said, there is no reliance on the main server. You can just go to any other peer that has that. And one of the other problems is censorship. So in the traditional networks, you can just be banned from using the server. Like let's say you abuse some terms of services of let's say AWS or any other cloud service. You might be banned. You won't be able to use it. The same goes for the governments. If they don't want you to use some service or access some data, they might simply ban it. One example of this was Turkey. On 29th April of 2017, the Turkish government banned their access to Turkish Wikipedia. It was probably because of the criticism of Turkish government and some of their other wrongdoings. In the 2020, it was unblocked, but it was still available, not through the traditional network, but it was available from IPFS. So you just had to connect to the IPFS network, and you could simply go to the network to the Wikipedia and access all of it. So yeah. And so you may be thinking, what is the difference between like IPFS and other P2P networks protocols, like for example BitTorrent? So you can think at it like IPFS is like one big torrent. So if you want to download something from the BitTorrent protocol, you have a torrent file and you download the whole file from this torrent. And on IPFS, you can look at all of the network like one big torrent that holds many different files, and you can just download some of them. And also one problem that IPFS solves is that you can, for BitTorrent protocol, you can create many torrents for the same data. They won't share seeders. Seeders are the people that hold the data and allow you to download it from them. And IPFS solves that problem because you don't have many torrent files. The whole network is one big torrent file. So yeah. And the other key point that was marked there was content addressing. And in the classical traditional networks, we are using location addressing. So we are using, you're going to the where it is, where then our resource is. So as an analogy, we can tell somebody that my phone is in my room, go there and get it. And we have like a map to where to go to that room, and we don't exactly know what is the phone, what is the exact phone. We know that it is somewhere there in the room. But about content addressing, you know what it is. So like I could tell somebody that here's my phone, a picture of my phone, go get it, and you will go and find it somewhere, like the exact phone. And the problem with location addressing, for example, are that problems with that are that sometimes you go to the URL and you find like there is no such URL, or there is no available content. There's one example taken from the IPFS blog. They stated that, for example, when you open the following URL of an image of astronaut Jessica Watkins from the NASA website, rely on AWS servers that host the NASA website. So we might think, okay, some part of the internet is reliant on AWS servers. So we might think, okay, they are pretty responsible, and it should be there. However, later, they state that the file is only available as long as the origin server hosts it. So the problem is when we go to the network when we go to the URL that is under this link, we can find that it is not found. So the problem is that with the traditional network, you can go to the website and you are probable to there's probability that you won't find the file. Because we are relying on the host, relying on the server maintainers that they will provide the file for us. So what is exactly the content identifiers in the context of IPFS? So in the URLs, we were, as I said, we were using the concept of where something is. We are going to the URL and we were looking for the part of the internet where we can find it. In the context of IPFS, we have the content identifiers. So, as I said, we find what something is. So we get the identifier of a file that we want to retrieve. This is basically hash and metadata of the file. They are in the form of like V0 and V1, and I will get into that in a second. So basically, earlier the V0, it was the content of the file hashed using SHA-256 with the data was encoded in protocol buffers, and it was all in base 58 BTC encoded. So the problem was that in the beginning it was a good solution, and later the IPFS developers started to notice that it may not be such a good solution. For one thing was that the whole hash was case sensitive. So in the case of browsers, it was fairly problematic. And later they developed the V1 version of content identifiers. And they were developed for the ease of use of other hashing algorithms, for other content representations. So you could use the representation of JSON, not only protocol buffers, and any other algorithms that you wished to use. So the V1 version uses three key concepts: multi-hash, multi-codec, and multi-base. And these are the parts of the content identifiers, parts of content identifier. So the first, multi-hash, basically what it is, you get as I said, you hash the file, so the zeros and ones on the right, and then you glue it together with additional metadata. So what hashing algorithm was used to hash this file, and how long is the hash. How the hashing algorithm is encoded. This is just the top of the list from the multi-hash GitHub repository. And there are many algorithms that are used, that can be used for encoding the data. And for example, let's say if we wanted to use SHA-256, so that would be the multi-hash of the whole file. So in the beginning, so on the top, we would have the 0x12 in hex and this in decimal 18, as in the screen. So we could see the row number 9. The SHA-256 is 0x12. So it is encoded in binary, of course. It is on the front. Later we have 256 as the length of the hash, and then we have the hash. As I said earlier, before hashing, we store data in a particular encoding. So it is another problem that we don't know what the encoding is. So the solution is let's glue it together with another prefix. So this is a data encoding algorithm this time. And also there are many of those algorithms. All of them are available on GitHub. So if we didn't know what data encoding algorithm we are using, so let's say we got the data, we wanted to decode it, and we assumed it was encoded in protocol buffers, and it was actually in JSON, we would get weird things. Another problem, so future proofing, giving a CID version. For now, version 1 is used here in the CID v1. It allows for any other possible standards in the future. So yeah. And another problem that we encounter here is that we don't want to store it all, the whole content identifier in binary. So we might want to store it as a string. And for example, we might want to encode we might have a representation like 11111, and this could be a valid string in base 2, base 4, base 8, base 16, base whatever. And when we are decoding the hash, the content identifier, we would like to know what base it was using. So yeah, as previously, we just glue it together with another prefix. So this time, in this example, the prefix would be p, and from the screen, also from the GitHub repository with the spec, it means it was in base 32. There are, like you can see, many of those possible encodings. It also is only at top of the list, so there are many possibilities, and it means that if you want to encode some data, and you will be using, you can use many different algorithms, so you can use many different possible encodings, and there can be many different hashes, but they may just point to the same file in the IPFS, because that's just basically different encoding. So how can we add a file to IPFS? For the beginning, in the beginning, like the file is chunked for the ease of storage. It is split into 256 kilobytes of data, and it allows for easier storage. Sometimes the chunks are the same. Like let's say in this example, we had this one big file, and it was split into the 4 smaller ones, and the first and the third one are the same. So for the problem of we can just address the problem of duplication here by just simply forgetting the third one and just encoding it as three pieces of three blocks, not just 4, because that would be, if we stored the four blocks, it would be redundant. So yeah. If also, supposing that we have two similar files that, for example, share most of the bytes, and I have one of them and I want the second one, we can just download one of the chunks that are missing. So you just need to download the different bytes. Also, the data is immutable, and once stored, the hash of the particular file will not change. It always will be the same. So same file uploaded. If you wanted to upload the same file twice, it would be only stored once, because the IPFS would get only one hash, the same hash. So the file wouldn't be stored twice. And how it is also stored in IPFS, it is stored as a unique FS file, and it is a protocol buffers-based format for describing files, directories, and symlinks in IPFS. And it is stored as a Merkle tree. So basically, under the hood, there are everywhere hashes, and they are based on hashes. But the whole concept is that the file is split into chunks, so that the bytes 0 to 200 are on the left, 200 to 350 are on the right. And so on recursively, they are split until the base is reached. But actually, it isn't a Merkle tree, it's a Merkle directed acyclic graph, just for the purpose of the duplication, like in the example before. Also, if you wanted to upload the directory to the IPFS, it would be very similar. We just need to know how to map the files to blocks, and we just do it by mapping the mapping file names in the directory to the hash mapping file names in the directory to the blocks using hashes. And what about the data that we get from that we get from the IPFS? So if you're running a node, the data is cached. Of course, we can reach it sometime, but the storage space is finite. So we may not store everything that we get, everything that we want to upload. So the nodes are using garbage collection. And there are many different algorithms used for that, but you sometimes may not want to delete all of the files that you have on your node, and you can protect the data simply by pinning it, and then the node will not be deleting the data that you are storing on your node. And on the other side, we have getting the data. So let's say we are the node and we want to get the file that is which content identifier is QMCAT. So what are we trying to do? We have to send the want list. What is want list? Want list is this is a simple description of what it is, but it mostly contains that content identifiers that we want to get from the network. And here simply it looks like almost like JSON, and we have the content identifier and that we want it. So yeah, how does it work in the network? So for my currently connected swarm of nodes, I can trade data with each node from this swarm, and we can choose the node that has data, and we send the want list to the node. Basically, you send it to every node in your swarm, and some nodes reply that they have that, they have the content, but some others say they don't have, and we later send the want list to those that have the data. Then the node as I said, it checks if it has the file. If it doesn't, it responds that it doesn't have the file. And then if it has that file, it decides whether it wants to send it or not. It is also based on that fact that sometimes there are many leechers. Leechers are nodes that simply retrieve that want the data but do not share anything. But there are many algorithms under the hood that are working on that. So yeah, later if the node decides to send the file, then it is sent back to me, for example. And then we check if this is the right file. How can we do that? When we get the block, the file, or the data that we wanted, it's encoded somehow. We get the content identifier of it. So we, using the fact that it was somehow encoded, like using some algorithm, let's say SHA-256, we can check how it was. It is actually the right file. If it isn't, we just go to another node. If it was, we then send the cancel request that tells other nodes that they shouldn't just keep sending the file if they have it to me. If the cancel request doesn't reach in good time, so the other nodes keep sending the file back to me. If I have it already, the node will just drop it. So the whole algorithm is called bitswap. You can learn more about it on the IPFS documentation. And also, there's a thing that we can store what files have. We can tell that what nodes have which files in our network, and this is simply stored in a hash table in like key value pairs. But there's a problem that we cannot store every piece of data that is in the network because the hash table would be simply too big. So the solution for this is distributing all of those tables to many different nodes from the network. So the simple overview of this is that you base the data where to store the data based on the prefix of the data and the node identifier. So let's say if we wanted to store QM full, we could store it in the QM footage node. This is just an example here. So how then we get to find who has the data? So if we, let's say, have QM full, we then find the node that is responsible for the info holding the info who has QM full and tell him that we want it. So if we want QM full, we then find a node and get the info who has the file. So what is happening when in all of our network, in the swarm of the nodes that we have, there isn't a node that has the QM cat, for example, QM cat content identifier. So as I said, it is based on the prefixes of the nodes and the contents. So let's say that we had a QM city in our node swarm, QM city node. So we would go and ask the node, do you have QM cat? And he would, for example, didn't have it. So he would reply, no, but I know QM cola. And then QM city would ask QM cola if this node has QM cat. No, but it knows QM Kate, another node. So then, this one. Then QM Cola would ask QM Kate if it has QM Cat, and let's say if it has, it would reply yes, I do. And then it would just send QM Cat to me as a chain of after the chain of requests. And then what would happen? Just this flow that I just described. So we would get if we decide if the node wanted to send it. If it sent it to me, then I would check the contents of the file and the hash, and then we'll set cancel request, and so on and so on and so forth. This is based on Kademlia algorithm. It was used for the distributing the hash tables from over the network. Yeah, it was just a basic overview. There are many more things going under the hood, and yeah, if you want, you can check out the white paper on the algorithm. So what about Filecoin in all of the IPFS? It is an incentive layer over IPFS. What does it mean? If we just join the network and we have to store the files, it may not be good for everybody, because we might be greedy. So we might not want to store everyone's files. Not everyone does it voluntarily. So it is an incentive over the IPFS to store the files. You basically rent your free space in exchange for Filecoin for Filecoin from other users. And basically, you rent the person who is using your free space is giving you Filecoins. You are basically a miner if you are renting your free space. And Filecoin uses proof of replication and proof of spacetime. What is proof of replication? The server proves to the client that it allocated a certain amount of storage exclusively for storing the copy of the file that it requested. And it also means that data can be easily accessed because of the proof. And proof of spacetime, and it is used for the storage providers that they are continuously storing the files, their data over time, and not simply discarding it. And periodically, providers create and submit those proof of spacetimes to prove the data is still being held and wasn't altered. So yeah. If you want to use IPFS and get some money from it, you just can become a miner. So you can just run your node in the meantime on your laptop every time it is on. So yeah, any questions? I'll try to answer them as good as I can.
I'll just give you this mic.
Yep, thank you. Maybe I missed it, so sorry if this is the case. The question is there any mechanism for protection for the case when I am as a user, I would like to use this IPFS to store my files, and then files are chunked, then they are going to different nodes, and then accidentally some of these nodes are just turning off. So it means it looks like my files become corrupted because chunks are not accessible anymore. So how is it prevented in the system?
Do you mean like some chunks are on the one node, other on the other node?
If I understood correctly, that when I upload the file, it is getting chunked, and then each chunk may be stored in different nodes.
Yeah, basically, it might be the case, but if the file is stored in one node, it's like using the Merkle tree. I think it is giving you the proof that it will be on the node. But I'm not sure. As I said, I'm not the expert on that. So sorry for not answering.
Yeah, thank you.
Thanks for a great presentation. I would like to ask, do you have any real use cases of using IPFS? For example, I don't know, NFTs, files For example, I think maybe, have you checked, maybe? Because I'm asking because I have checked a price of Filecoin. So it is a cryptocurrency in exchange of giving a space. And I have found that it has a price over $150 2 years ago. And now it is still dropping. It is about $6 now. So I'm a little bit confusing that maybe it is not real cases for use this. For example, application for Filecoin blockchains.
As far as I know, on the Filecoin blockchain, there are stored like the NFT collections. That's one of the cases that I read about. And on the whole IPFS, as I said before, you can just use it as an archive for the internet. One case of this was funding of the founder of the founders of IPFS and the Filecoin donated a huge amount of money for the Internet Archive project to use the Filecoin blockchain and the whole IPFS system to basically archive the internet. And as I said before, one of the cases for the IPFS was like the Wikipedia in the Turkey, and for many other countries that have censorship. So.
Any more questions? Okay.
So the first point is, you said that this is a centralized network, it's bad. So let's say you ask Google Drive for the file, but actually in every fang, like under the hood, there is some kind of small decentralized network, like because of the data replication, and so is it actually bad? And the second point you asked, you said about the censorship. I see the second, how would say, side of coin. Let's say you rent your free space and someone asks you to host some forbidden files, I would say, and so how to deal with that?
Yeah, so for the first point, it wasn't my intention to say like the centralized network is bad and the IPFS is good, like the one side and the other of the coin. But like the centralized network has some downsides. Also, IPFS has some downsides. For your first point, it also can mean that if we go to the Google Drive and store the file there, if something bad happens, for example, like the whole Google company dies, it might be a possibility. Like it may not be in the nearest future, but sometime, somewhere, it can happen. Then your data replicated on Google Drive on many different servers would mean nothing, because you wouldn't be able to access it because Google would be dead. And for the second point, yeah, that's tricky. I don't know how to address it. I think there was some problems on this on Ethereum, but I wasn't investigating how it was solved. So yeah, I get your point.
Yeah, thanks for the talk. By the way, to answer the question about like legal stuff, well, I guess if you would be the one that would be hosting something and like an agency would come up to you, a government agency, that you have to, like with a request to, drop this file out, then you would probably drop it out. But you were saying about the content addressing, so if I understand correctly, the main point of it is that you can basically confirm that the file you downloaded is the file you wanted to download, right? But my point is that you said also that when I'm maybe that was about the upload, that then like when I'm uploading a file, I cannot upload the same file twice. But then if you go to the content ID stuff and look how it works,
you have this code for the hashing algorithm, and you can like upload the same file twice with a different hashing algorithm. Is that the case, or is it not?
No, I think it's not. I'm not 100% sure how does it work, but for some nodes they serve like the data encoded in one way, other nodes serve in other way. So
if those nodes would basically exchange the same files with each other, they would not maybe not recognize they store the same data.
I think they do it somehow under the hood, but I'm not, like I said, I'm not sure how exactly does it work.
And the content ID stuff, like the format of it, had like a hashing algorithm, which was the code or enum, and then there was length of the hash, right?
Mm-hmm.
Why do I need the length of the hash if I have like a hashing algorithm that I know of its length? I mean, it should be variable based on the hashing algorithm if it needs a hash length field or not. And I guess that they may eventually end up with another version of the ID that would drop this out because they are wasting space.
Yeah, it's probable. I wasn't thinking about this, and you have a good point. And yeah.
Also, what happens if you upload a file and say that the hashing length is different than it is? It's probably validated.
Could be. I'm not sure, as I said. But yeah, it's if they like I said, they have the field for the new versions, so it could be probably fixed in the future. Probably since it's working right now, it may be good, but I didn't investigate it that much.
Also, if we're speaking about Filecoin, I guess it may be good to say something about like alternatives, like StoreJ or some different ones. Do you have any opinions on them?
Not much, because I just investigating the Filecoin. But I don't know, I cannot answer this question.
Sure, because it may matter for people who want to rent their space.
Yeah, exactly.
Because they may earn more money on other solutions, maybe. Thank you.
Thank you.
Do we have any more questions? Oh, okay.
Hello, I'm a little bit confused how the mining on the IPFS works, because in other chains we use compute power, which is stateless for mining. And if I understood you correctly, we use disk space for mining in IPFS, which is stateful. So if, for example, we will somehow lose the data on all nodes, what is the background of the mining in file system? How do we mine in this IPFS?
So I think that since the nodes are uploading the proof of replication and proof of spacetime, it is based that if you want to store some data on the Filecoin, you would go to the nodes that are most reliable. So they constantly upload the proof of replication, the proof of spacetime. And if you were a node that wasn't just as reliant as others, that I think the data wouldn't be simply stored on your node. As for the mining, I'm not sure, because as I said many times now, I'm no expert, but you just might not get any coins if you are not reliable enough for the whole network. And yeah.
Thank you. Is there some way to have mutability inside? So, for example, can I save a document and then edit it in the way that I would see the change? Something like a proxy on Ethereum?
Yeah, IPFS has some built-in mechanisms for that. It works similarly to Git, where you have versioning of the file. When you have basically let's say you have a pointer and you just change the pointer to the new implementations of the file, implementation, like the file, the different hash of the file.
Okay, thank you.
All right, I think we don't have any more time for questions. Thank you, Tomasz, for your talk. And yeah. So now for the last talk, Antoni Żółciak from Aleph Zero will join us for a talk titled Layering Up Privacy, Enhancing Trust, Transparency, and Compliance. Off to you.
1, 2, 1, 2. Does it work? Can you guys hear me okay? All right. I'm gonna go a bit on a higher level and not be so technical. Present. Okay. And I'm gonna just try and give you an overview of what we're doing with Aleph Zero, what is it, where we're going, and hopefully it's gonna be interesting enough for you. In case there are any questions, obviously ask away. So we're, just to oversimplify things, we're a ZK blockchain infrastructure. So there are two problems that we're aiming to solve. And the first one is just overall performance of blockchains, and the second is how do you achieve on-chain privacy in a way that is sustainable from both a compliance and a UX standpoint. And we started back in 2018, actually here in Kraków, with the goal to create a new consensus protocol. That's what we thought was the most important thing as far as the sort of the basic network infrastructure, and we somewhat still do. So we started with that, then we combined it with a substrate stack, and then we launched the network. This is what we have currently. So technically it's an L1. It has its own consensus protocol called Aleph BFT. It took us around 2 years to develop this. And then this was combined with the substrate stack, which is the stuff that powers all the Polkadot ecosystem. So we kind of swapped the original Babe and Grandpa stuff for our own consensus. And besides that, we're working on ZK and MPC applications on top of the network. Now the current network is WASM only, so we're not EVM compatible, which poses numerous challenges, especially from a distribution standpoint, from an adoption standpoint as well. So this is one of the priorities that we have for this year. And it's going to debut quite soon, actually. And then also the important thing is that let's call it privacy features that we're working on, we want to also export them to an extent to the wider ETH ecosystem. As far as what's the current state of the network and the ecosystem. We're at around 55 people in the core team. There's over 50 external teams involved in the ecosystem build-out. That doesn't mean that we have 50 plus apps that are mature and about to deploy. It's less than that. It's between 20 and 30. And it's anything from smaller startups to let's say, applications that are more mature and with some traction or some adoption in other ecosystems that they're looking to expand to the network. As a sort of public and open source L1, we need to have validators. There's over 160 of them. Vast majority are run by our community. We do have some enterprises that are validating the network, which also is going to lead me to a segue in this talk in a bit. And then we have a community that was primarily built out in an organic fashion. It's not the largest, but they are definitely very engaged, I would say. Now, this is sort of the just a logo show, I guess. But the goal here is that we kind of managed to get involved with a few bigger names. This is actually the lineup for supporters of our last hackathon, where the priority was to design sort of Web3 telco use cases. And we ended up with over 30 submissions, which was somewhat unexpected because we were betting for less. So that's nice. And then as far as the use cases, which is what can you actually do with this L1 and what can you do with the entire network. So we do have basic DeFi primitives like liquid staking, and the DEX is coming quite soon as well. We've deployed our own sort of bridge between LF0 and Ethereum. It's like a Guardian-based bridge. So end of this month, we're gonna see some traction on the network as far as actual usage. Then we have what we call like Web 2.5, which is a very generic term, but I guess it kind of encompasses the like conventional use cases that can benefit from crypto or from Web3. And one example here is Darkverse. It's also a Polish team that's working on like a very dark RPG game. Jacek Dukaj is writing a script, and then a team that was involved in certain projects for like Cyberpunk 2077 and The Witcher is working on the gameplay and the overall production. And the idea to use blockchain there, or how to enhance it, is that if you actually establish an in-game economy based on crypto, then how much more engaging this can become without turning into an unhealthy casino. So basically, this is what we're trying to experiment with there. And then we have the enterprise front. So we're working with two telco companies at the moment. First one is Deutsche Telekom or T-Mobile on some other markets. And the second one is Saudi Telecom. And those relationships started with them just onboarding to the network as validators. For us, it was quite of a big deal because it was way back when the sort of the privacy on a public chain was under heavy regulatory scrutiny. And now we're looking into various use cases that range from, for instance, an enterprise wallet on a public chain that can utilize some of the on-chain privacy that can be then implemented into an enterprise workflow to effectively somehow boosting. For instance, Saudi Telecom has something called SDC Play. It's like their own version of Steam on the MENA market. And we're looking at how this could be, for instance, used as a distribution channel for Web3/crypto products. After like over a year of working with different teams at developing use cases, these are some of them, and like not all of them benefit from let's say the privacy concept. Some of them are more akin to I would say the equivalent of primitives known from other ecosystems, but since we use a different tech stack, they had to be rebuilt. But just as an example, like stuff like IDOS, which is the last on the right, it's an approach to solve the interoperability of verified credentials. So how can you basically work with KYC, KYB providers to ease the burden of user experience for crypto users across many different platforms. Right now, if you want to use something that has a custodian element to it, you do have to essentially just KYC all over again, like all the time in all of the products. With IDOS, the goal is to have like a universal profile and then reuse it within the operators or product connected to IDOS. What we're doing there is designing a ZK ID system, which means that if it's done properly, you shouldn't even need to have to prove your identity and disclose all the data that of who you are. You would just have to prove that, for instance, you're not on sanctions lists, that the provenance of your funds has been legit, so to speak, and so on. Then we have Syncra as an example. So this is a use case for private voting, meaning that it's a no-code solution for DAOs. And the idea there is that how do you establish a private governance for different protocols? And then if you're interested in learning more about this, then we do have an entire ecosystem webpage where you can find all the use cases that we're working on. One of the interesting ones is also a native stablecoin. So it's called OneUSD. We're working on this with a company called Archblock. And the idea there is to experiment with a privacy-enhanced stable, meaning that how do you effectively use a stablecoin for payments? And you can technically just go ahead and use USDC or USDT, shield them, and use them that way. With this, we're trying to design something a bit more convenient. Yeah, we do have an ecosystem funding program. So this is an initiative that consists of like a combination of grants and incubation. So if you're interested in building something, I'm not sure what level of like involvement in the journey or like Web3 you folks have. But we're now incubating the aforementioned like 20, 30 different teams. So very happy to also talk, and if you have any ideas for projects, we'd be more than happy to support. Yeah, that's the URL for the broader ecosystem. And now, like, this is also on a high level, but we think this is somewhat important, especially when we're talking about on-chain privacy in a public environment. So we've seen multiple examples of projects dealing with this particular challenge, being having problems on the regulatory front. So our approach to this has been to first integrate with CoinFirm, which is essentially a blockchain analytics company similar to Chainalysis, and then with IDOS. So all the privacy features on Aleph Zero are going to be gated, meaning that you have two modes of operation on the network. First one is your standard transparent, akin to Ethereum, Solana, or any other permissionless network. And then for the privacy features, there's going to be this entire ZKID system that hopefully is going to be manageable from a user experience standpoint. It's not ideal, but with the current regulations, we do think this is the best possible option. Yeah, so this is like a very, very short overview of what we're doing. Thanks, and if you have any questions, happy to answer.
Do we have any questions? All right. Thank you, Anthony, for your talk.
Thank you.
All right. That was the last talk for today. I think the pizza is already here, so stay with us for pizza and to just chat. And I'm assuming you're all following us on our socials, but just keep doing so and stay tuned for more information about upcoming meetups. Thank you.